Hello, my name is Aaron. Welcome to this video on LeetCode 621 Task Scheduler. So the question asks us you are given an array of CPU tasks, each represented by letters A to Z, and a cooling time N. So here we have two inputs. And then it says each cycle or interval allows the completion of one task. Tasks can be completed in any order, but there's a constraint. Identical tasks must be separated by at least n intervals due to cooling time. And the goal here is to return the minimum number of intervals required to complete all the tasks in our task list. So just to make sure we understand the question correctly, let's go through some of these examples. So we're given this input here, tasks equals AAA, BBB. So there's 6 tasks in total. These are tasks of the same type. All of these are A's, these are B's. So there's 3 A's, 3 B's. And then the cooling time is 2. And so what this means is for all tasks of type A, there must be at least 2 gaps, 2 spaces in which other tasks or an idle time, an idle interval occurs before another task of type A happens again. So the explanation here shows that a possible sequence that solves this problem is A, B, idle. So that's an empty interval, no task happens here. And then A happens again, and so there's 2 intervals in between. And then it repeats on itself, A, B, idle, A. Again, creating that separation between the A's, but also the B's. So B, idle, A. That idle plus A makes a separation of 2 intervals. And that happens again here. B, idle, A, B. And there's a separation of 2 intervals between those 2 B's. So here's the problem statement, just restated a little differently. I framed it in terms of an input and an output. So we have 2 inputs, again, our list of tasks. And then we have a cooldown time, N, like before. And then our output here is the minimum number of intervals required to complete all of the tasks, just like before. And so there are various different approaches to this problem, actually. Some solutions use a priority queue. I will be using a greedy algorithm. And a greedy algorithm is basically just an algorithm that makes a series of iterative and myopic decisions in order to reach the solution at the end. And to explain what I mean by that, let's just take a look at an example. So if we have this as an input, and let's say we have a cooling time of 2, one insight you might think is, okay, what if we just rank all the different task types by their frequency? And let's try to build a schedule by looking at the most frequent tasks first, and then iteratively add in the less frequent tasks until we reach our least frequent tasks. And so, for example, in this case, we only have 2 tasks, A and B, or 2 types of tasks, A and B. We really have 5 tasks here. But let's take a look at our most frequent task type, A. And let's just say the highest frequency equals 3. Let's just say we're going to call HF our highest frequency in the list. Right? So if we have this, how much separation, or what does our schedule look like at the very least if we have 3 A's and 2 intervals for cooldown time? Well, it'll have to at least look something like this, right? There can be any number of different tasks in between them, but we know at the very least we're going to have this much amount of time. And this is going to be 7 intervals, right? So if we know nothing about the what tasks follow, but we know that this A is going to be the most frequent task, we know that A has to be separated at least by this much, right? It could be like something like this. But in the absence of information about the rest of the tasks, and we're just assuming, let's just take the most frequent task and let's just build a basic schedule off that, and then we could fill in the less frequent tasks afterwards. This is what it must look like. Okay? So that's our insight into the greedy algorithm. Let's imagine what a schedule looks like with the most frequent element in consideration, and then let's try to fill in the remaining tasks that are potentially equally as frequent, but no more frequent than the highest frequency task, which in this case is A. And so for this example, we would fill in B's accordingly. Right? So B would go here, and in order to have enough separation, we put B here again. Now we could put that second B somewhere like here, but that would increase our schedule time. It would be 8 intervals. Since we can optimize it like this, we just keep it in that empty interval between the A's. So this is now conducive to case analysis. Let's just start thinking about various inputs and see how, based on different frequencies and different cooldown times, the potential possibilities for filling in the remaining empty intervals look like. And so we'll use this next example. Let's take a look at the array A, B, B, B. So note here, in comparison to the first example, that the two task types have the same frequency. So we can just arbitrarily pick one to be the first one that we put in our schedule, and we can, let's just say, let's use A again, and let's have a cooldown time also of 2. So just like before, we have this basic kind of skeleton schedule that we might have to expand further or add more intervals in between, but we know it must take this long. It cannot take any shorter. For example, we cannot have a schedule like this that's 6 long. Okay? Now, like before, we want to fill in the remaining tasks. But here, we have a task of the same frequency as before. So note what happens. We have to fill in that B, and there's 3 of them. Now, there's 2 of these kind of, I don't want to say intervals, but segments of the initial schedule, or kind of primitive schedule. But there's 3 different B tasks. So what we have to do, unfortunately, is extend it past this last A. And you'll notice, so long as there are empty intervals of this kind, and the list of highest frequency elements continues, so let's say we have something like CCC in our list, then we're going to have to do the same thing. We're going to have to fill in the remaining intervals in those segments and then add 1 extra task at the end. Okay? Now let's look at another example. So that example showed what happens when we have tasks of the same highest frequency as the highest frequency task we arbitrarily chose. So what happens if it's less? Well, just like before, let's just say we have something like A, and then B. Like that's our input array, and then our cooldown time is, say, 2. So we have something like A, and then we have this B. So where does this B go? Well, it just goes here. So that makes sense. So what's the difference between this example and the one that came before? Well, here, we're not actually introducing any new intervals. So remember before, we have these new intervals that are introduced every time we have an element of that same frequency as the highest frequency. Remember, the highest frequency here is 3. And it happens that there's also another task of that same highest frequency. So let's say this is also the highest frequency, the frequency of this B task is equal to the frequency of A task, which is equal to the highest frequency. So no new intervals are introduced here. So actually, what we actually return here is just 7 intervals. Whereas up here, we've added new intervals because we have to accommodate for those extra tasks at the end. And we're going to say this is 7, 8, 9 intervals. So what we take from this is that we should expect, if there are multiple tasks of the highest frequency, that we're going to have to actually introduce new intervals. Whereas so long there are empty intervals remaining, in this example, for example, we're not going to actually need to add new intervals. We're just going to use those empty ones until they're expended. Now, what about this case? What if we have, for example, the input A, B, 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 C, C, C. And our cooldown time, let's say, is 1. Then our initial skeleton schedule, the minimum schedule that we have, looks something like this. Right? Because every A, the most frequent element is A, and every A must be separated by at least 1. So it takes at least 10 intervals to complete the schedule. Then we have to worry about our other tasks, and we have to start filling them in. So we start filling them in, B, 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 naturally, so we retains that separation. But then we get to C, and C only has one interval remaining. That's empty. So we put it in the empty interval. Okay, but we still have these two C's to put in our schedule. And so here, we actually have to put C back into a gap earlier on. And it doesn't really matter where we put them as long as they're separated, but we can just say, let's go A, B, C, and then insert a C there. A, B, C, insert here. So actually here, like our first example, or sorry, our second example up here with our 9 intervals, with multiple letters of the highest frequency, we're going to actually have to introduce new intervals here. But let's formalize that a bit. Let's try to think of an expression or some kind of mathematical way to describe how many new intervals we would have to add in this case. So when we have this new intervals, when we have this situation in which you must fill in an empty interval and then add your letter to some other part of the schedule, we can say, okay, let's consider how many intervals were empty before, right? So before we add this C, there were, let's just use, empty intervals, there was 1. And what's the frequency? All right, let's just say, for shorthand, frequency of C is equal to 3. So we know that we can put exactly one C into that empty interval, right? And then our new intervals, we're going to have to create one new interval for every C we cannot put in the empty intervals remaining. So let's actually call this empty intervals remaining. So new intervals is equal to empty, or sorry, the frequency of our letter in question, and then that subtracted by the empty intervals. Right? And so we get that expression, and we evaluate it, it's 3 minus 1 equals 2. And that's exactly the amount of intervals that we had to add in this case. Now, let's take a look at a final example. What if we're trying to add in a letter, but the empty intervals remaining are 0. Our schedule is already kind of saturated. So let's take this example, AAA, let's do BB, B, and then C, C, D, D, right? And then we'll do N equals 1. So A, let's choose A to be our highest frequency one. It could be B, but let's just say A like this. And then we have B, B. Right, so like before, we have this BBB example, so we get BBB, and we have to add that B to the end. So this is the same situation as before when we had to add this extra B in when there's multiple letters of the highest frequency. But here, once we get to C, our third most frequent letter, where do we put that? Well, we could simply add C into these regular intervals that happen for every A. So for example, here, we filled in those gaps. Let's add a C over here. And then we filled in the gap. And then after that gap, let's add in another C. And you can convince yourself that that's actually true. Once the schedule has been saturated, all the empty intervals have been taken, the remaining letters must be able to fit in some pattern, in some fashion, such that they are separated by the cooldown time. And that's because intuitively, the more frequent elements have already been separated by that much. So there actually is enough space for these less frequent letters to fit in with that cooling time allowed. Okay? And then similarly with the D, we can just add in those Ds here. Or sorry, not over here, right after that C. And so the new intervals here, and you can tell I'm kind of getting at the code in this notation, the new intervals here is equal to, well, let's think about it. Let's just say we know that the empty intervals remaining are 0. So the new intervals that we must add are simply the frequency of whatever letter that we have at hand. So for example, if we're at the step of filling in C, and we know that the schedule is already saturated, there's no more empty spaces, we're going to have to add exactly the number of C's in our input array into the schedule so that it increases the schedule length by exactly F sub C, which is equal to, in this case, 2 intervals. So that's the increase, 2 intervals, and the same goes for D. Okay. Now we can summarize and think about how our algorithm is going to look in light of these cases. Right? So basically what we just did in all these different examples is think about, at some point, I'm going to have to fill in a potentially equal frequency letter or less frequency letter into our schedule. And we're going to have to ask 2 questions for each letter after the most frequent one. Right? So there's going to be 2 questions. 1, how does it change? How does adding this letter into schedule change the number of empty slots? And then 2, how does it increase the number of new intervals? And I should rephrase here, how does adding this letter into the schedule decrease the number of empty slots? Because we're always going to decrease the number of empty slots if there are empty slots available. That's part of our greedy algorithm. Okay, so now we can think about pseudocode, right? So what are we going to do? Well, first, we're going to need to sort our task types in decreasing order of frequency. And then what we're going to need to do is iterate through that list and then determine how each letter, after adding to the schedule, changes those 2 questions above. Right, so it's going to be 1, new intervals. And then 2, it's going to be empty intervals remaining. Okay? And then finally, we're going to just return the number of intervals in our final schedule. Okay? And before we dive into the code, one final thing, let's just think about the decision tree, right, that we have here. So we've gone through all these examples of given a letter in our iteration of that for loop. What does adding that letter impact in what way does adding that letter impact the number of empty intervals remaining, as well as are there any new intervals that must be added? And that question at each letter in our for loop will actually boil down, it must boil down to this kind of partition of the search space. So it's going to be something like, okay, at this current point in our schedule, let's ask, do empty slots remain? Or are there no empty slots? Okay, and if there are no empty slots, then we can do what we did in this example, right? So let's just say at each letter X in our, all right, let's not make this confusing actually. Let's just keep it like that. At each letter in our for loop, when there's no empty slots remaining, we have to do what we did in this last example, is literally just add the letter to the schedule as we did with C and D. We have to put them in like some sort of gaps, but we know that it will fit. Like it'll be separated by enough intervals in between, if we just follow the pattern of filling in the previous letters. Okay, so that's what happens when we have no empty slots. We just add in those letters and we increase the number of, increase the size of the schedule by exactly the frequency of that letter. Oh, sorry, up, schedule. Frequency. Okay, so that was our fourth example, or our fifth. And then, so in the case that empty slots remain, there are kind of two breakdowns of this. First is the letter has the same frequency as the highest frequency. Right, so that's one option. And then the letter frequency is less than the highest frequency. All right, so the letter has the same frequency as the highest frequency. That's our example here with, you know, this 9 intervals. Right, so this BBB comes in, and what we observed is that it fills in all HF minus 1 kind of segments available for those empty slots, like this one. So there's HF minus 1, so 3 minus 1 equals 2. So there's 2 empty slots it filled in, and then it added a new one. So this increases intervals by 1, decreases empty slots remaining by HF minus 1. Okay? And then there's these two subcases when the letter's frequency is less than H, the highest frequency. So, like before, we saw that in this example, we simply just fill in an empty space, no new intervals added with that B, right? No new intervals added, we just decrease the, so let's say there's two cases. There's all, the frequency is less than the number of slots, less than or equal to the slots remaining. So in that case, we only decrease number of remaining slots by the frequency. But there's this case, this case here, where we have that C, right, and it fills in a remaining slot, and then while filling in, the schedule becomes saturated, so we actually have to add in these new slots, or these new intervals, and we'll say that this case is the frequency is greater than the number of slots remaining. So there's the possibility for overflow. And in that case, we set empty slots remaining to 0, and we add in, what was that formula we had before? You would have to add in frequency minus minus new intervals. Okay. And for some of you astute watchers out there, you might think, okay, well, why is this true? Why is it the case that when the letter has the same frequency as the highest frequency, it increases the new intervals by 1 and decreases the empty slots remaining by the highest frequency minus 1? Can't there be a situation like this in which that highest frequency fills up partially and then must wrap around and we have to create new intervals after the schedule is saturated? And the answer to that is no. Actually, that's not possible. And the reason why is because if you assume, for example, that this were possible, that a letter with the highest frequency fills in partially the remaining empty intervals before becoming saturating and needing to add in new intervals, then that means some letter before it, and by before I mean literally in that sorted order that we're talking about here, sort our task types in decreasing order of frequency. So one that came before it must have filled it in partially. But we also know that if it came before it in the list, it must also have the same frequency because it is the highest frequency, right? If it's sorted in decreasing order, it must have the highest frequency. So any task that came before it must also have the highest frequency. And we know that if it were the case that there's still empty remaining slots before this iteration, then it must have filled in evenly among those HF minus 1 segments of the schedule. So there are no uneven filling ins once in any case of the letter having the highest frequency, since all of the ones before also must have had the highest frequency. For example, it can't be the case that you have something like A, B, B, and then C, C, C. Right? This does not happen. You cannot have A, and let's say n equals 2, A, and then B just fills in partially. Because we mandated that the highest frequencies come first. So C, C, C must have come first, meaning it must have filled in this way. All right. So that is the case analysis for how we're going to actually break down each iteration and analyze it. And so the idea is, for each letter, we're going to count how much these two fields above, right? So the number of empty slots and the number of new intervals, how much it changes on each letter. And we'll have an initial count of all these, the number of slots, and also the initial number of empty slots. And then we'll iterate through all of the letters and then look at their frequencies. And then finally, we're going to, during those iterations, we're going to actually update the new intervals added and the empty intervals remaining. And then finally, we're going to return the length of our schedule after that. And so interestingly here, and to our advantage, we don't actually have to build our schedule because our question is asking us the minimum number of required intervals that we need. It doesn't say return me the actual schedule. So we can just keep track of these counts. We don't actually need to have a data structure that represents the array of the final schedule. We just need to keep track of a number. And so in that, it makes our life actually a lot more simpler. And we'll see that in the code. All right, so let's code up our solution. And remember, we have those 3 steps. So first we have to sort our tasks in decreasing order of their frequency. And then we have to iterate through that list. And then finally return, after doing all of our computations during that for loop, what is the number of intervals needed. Okay. So let's start by trying to get the frequencies of our tasks. So we have this. Let's initialize a dictionary, and then we'll say let's iterate through all the tasks. And remember, our tasks array is simply this list of characters. So we don't know the frequencies yet, but we have to compute that. So we'll iterate through each letter. And then we'll say, let's add it to this dictionary in which the keys are the characters. So for example, a key might be A. And then let's count how many there are. So go through each one and then add 1 to the value assigned to each key, which is the character. So that gives us the count. And this freaks.get here helps us handle that key error in which a key might have not been seen before. So for example, if we're done with the A's and we're onto the B's, we've never seen it before. Calling this freaks task, indexing that key would return us a key error because that B would never have exist. But this method .get in Python will automatically handle that error and then assign or insert a new key and then assign that value equal to 0. So in that B example, this would give us 1. That would be the B would be initialized to be a frequency of 1. And then we'll do a little Pythonic magic here. We'll sort that dictionary and we'll put it into a list so that it's a list of 2 tuples in which the first element is the character and then the second element is its frequency. So we'll do something like this, items, and that gets us the key value pairs. And then we'll do a little anonymous lambda function in which we simply map the to the second element, and then we reverse it because sort automatically sorts in increasing order, but we actually want the list to be in decreasing order. Okay, now that we've got our sorted list, we want to think about what is our highest frequency, first of all. And since it's sorted in decreasing order, we can simply just look at the frequencies list, get the first tuple, right, the first character and its frequency. All right, so we've gotten that, and then within that tuple, we want to get its frequency in the second element, so we index 1. And so that example of AAABB, we would be looking at a list of tuples A3, and then in our second tuple will be B2. And then we're going to want to think about how many intervals are needed at the very least. And so that's that skeleton that we were talking about before. Well, let's think about it. So we would actually have to think about how many degrees of separation you need, how much cooldown time you need, and how do you apply that over the most frequent element. So it turns out, and you can kind of figure this out through observation, that the formula is this. So we need no fewer than these many intervals to build our schedule. We might need more, and we'll see if we need more through the for loop. And then we're going to think about how many empty intervals are remaining. And so we know when we initialize the skeleton, we have these empty intervals. And it turns out, if you just count them, and if you go back and look at the examples that we went through, this is actually the expression for determining them. So the highest frequency minus 1, and that gives us basically the segments between all the A's and that skeleton A, right? And then you multiply those segments by the cooldown time. So basically it's the length of that segment times the frequency of those segments. Okay, now we're ready for our loop. And we'll actually start with the second element in our list because we already know about the frequency list, right? We already know the highest frequency element and how much that contributes to the intervals. We literally just counted that with the intervals needed. So we're past that initialization step. Now we actually want to look at all the intervals that come after the highest frequency interval, which is chosen arbitrarily in this case. So there might be others with the highest frequency. Okay. And just for a shorthand, since we're doing this for loop through range and we're going through indices I, let's just get a quick and dirty way to keep referring to the frequency of our current character without needing to type in that kind of semantically opaque freaks list I1 expression. And then we're going to check whether, according to our decision tree, remember that first branch, right? Are there any empty intervals remaining? If there are none, all we have to do is simply add to our intervals needed the number of elements or a number of tasks, the frequency of their tasks at hand, and then we can keep going. That's because we know after all of our empty intervals are used, all the tasks that come after that, regardless of how frequent they are, they're just going to have to be added into the count of intervals needed in the same way. And then this is our next split in the branch. So if the current frequency is equal to the highest frequency, we actually have to increase the intervals needed by 1. And then we're going to have to decrease the empty intervals remaining by this number, as shown before. And so in this case, if the current frequency is equal to the highest frequency, we handle it that way. The other case is that the current frequency is less than the highest frequency. Remember, the current frequency can't be higher than the highest frequency. We already determined that. That would pose an obvious contradiction. So we have to check now if the current frequency is greater than the slots remaining. Like, can we put this into all the slots remaining? And if it is more frequent than the empty slots remaining, then there's going to be that leftover that we have to insert to the earlier parts of the schedule. We don't actually have to insert it in this case. We can just reason about how it changes the amount of intervals needed. And so the amount of intervals needed, and this is our running count. Before we were talking about tracking like new intervals, but we're just simply adding to a running count of our intervals needed here in this code. So we add the current frequency subtracted by the empty intervals remaining. And then finally, empty intervals remaining, we set that to 0. So it'll never have any chance of being populated by tasks in the future. And then in the case that the current frequency is less than or equal to empty intervals remaining, then we simply subtract the empty intervals remaining by the current frequency. And that's our for loop. That's all. That's all the arithmetic we need to do to track the intervals remaining, the empty intervals remaining, and also how many intervals, new intervals we add. And finally, we just simply return the intervals needed. Okay, so this is the entirety of the code. And I'll do just a quick runtime analysis of this code. If we just go down, we'll see that this for loop is O of n. So n is going to be the size of our tasks array. And we'll say, okay, well, this is O of n because we just create a dictionary by iterating through each list in the, each item in that list, our input list. Our sort method actually requires n log n times, so that's more than this O n. So this is the dominant factor so far. And then we do a bunch of O1 initialization steps. And then these operations within the for loop, these are all constant time operations, but the for loop itself runs for as long, it is proportional to the length of the frequency list. So this is also O of n. So it's O of n plus O of n log n, and then big O of n here. So our overall runtime is determined by the runtime of the sorting algorithm n log n. So this is a pretty fast solution. And then in terms of extra space, we're going to be using that frequency dictionary. So that's O(n) extra space, in addition to all these constant factors, these constant variables that we just track the numbers with. And that's not very significant in comparison to the dictionary. And so that's all that needed. This is the solution using the greedy algorithm. There's other ways to write it up, but I hope you learned something and I hope you enjoyed.